today's class. Today we are going to discuss the Lagrange multiplier theorem. First of all, we will state that theorem, then we will prove the theorem. Theorem. Let S be an n-surface. Let S be a n-surface in Rn plus 1. S equal to F inverse of C, where F is defined from U to R. F is defined from U to R is such that del f of q not equal to 0 for every q belongs to S. Nothing but our surface definition. Now suppose another function g from u to r, okay, same u to r is a smooth function, and P belongs to S, is an extreme point of G, G on S, what's the meaning of extreme point? Extreme point means that is either G of P is less than or equal to G of Q, that is either for every Q belongs to S, or, and the condition is G of P should be greater than or equal to G of Q for every Q belongs to S. Then we will say that this P is an extreme point of G. Then there exists a real number. Then there exists a real number lambda such that del G of P is equal to lambda times del F of P. So this is the condition. Now the number lambda is called Lagrange multiplier. So this is the statement of theorem. So what does Lagrange's multiplier theorem says? Theorem says that you are having S as a surface, then you have got a smooth function for defining the surface, right? That is F. Now suppose there is another function G from some U to R, which is also smooth, and that has got an extreme point at P. Then we can write del G of P as lambda times del F of P, and this number lambda is called the Lagrange multiplier. So we want to prove there exists such a lambda. So proof: the tangent space to S at point P. First we are considering the tangent space to S. S means surface at P is SP, and we know that this SP is equal to del F of P perp, that is set of all orthogonal, or you can say that it is having those plane which is having the dot product with del F of P as 0, right? So we are considering all the vectors which are perpendicular to del F of P. Hence, why should be SP perp then? It's perpendicular or it's orthogonal vector. That means del F of P, right? Then is the one-dimensional subspace of Rp n plus 1 spanned by which vector? Del F of P, right? So SP perp is the one-dimensional subspace of Rp n plus 1 spanned by del F of P. Then del G of P is equal to some lambda times del F of P whenever your del F of P belongs to this space, right? For some lambda belongs to R, if condition is the if del G of P belongs to SP perp. So this is the condition. So we will prove that del G of P belongs to SP perp. That is, if and only if del G of P dot V equal to 0 for all V belongs to SP, right? But each V belongs to SP is of the form some alpha dot of T, some T naught, alpha dot of T naught for some parameterized curve, alpha from I to S, and T naught belongs to I with the condition alpha dot T naught, sorry, alpha of T naught, not alpha dot, is alpha of T naught okay, alpha of T naught equal to P. Why we are writing like this? Because SP means it is the tangent space, and we know that the velocity vector belongs to the tangent space. So each vector in the tangent space can be written as the velocity vector of some parameterized curve. So this is equal to this. So since P equal to alpha of T naught is an extreme point of G on S, but we can have is F naught is or the T naught is an extreme point of T naught is an extreme point of which function? G composition F of T, right? So G composition alpha. Say extreme point of G composition alpha on I. G composition alpha on I. Hence, what you are having is G composition alpha dash of T naught is equal to 0, right? That is, using chain rule, this will become del G of alpha of T naught dot alpha dot of T naught equal to 0 by chain rule. Right? But alpha dot of T naught means nothing but V, right? V is of the form alpha dot of T naught, right? So we can write this as that is del G of alpha of T naught is P dot V, right, is equal to 0 for all V belongs to SP. For all V belongs to SP. And so what we can conclude is del G of P is equal to some lambda times del F of P for some lambda belongs to real number, hence the theorem. So we have proved the Lagrange multiplier theorem. So the Lagrange multiplier theorem says that whenever you are having a function, a surface and a smooth function on the surface G, then if G has got an extreme point, then del G of that extreme point is equal to some lambda times del F of some that extreme point. So we have proved the theorem. Here is the remark. If S is compact, compact means closed and bounded, right? So closed and bounded. We are talking about compact surfaces. So it is closed and bounded surface. Then every smooth function G from U to R attain a maximum on S, attains a maximum on S and a minimum on S. This is somewhat analogous to the result you have studied in your real analysis or topology class as whenever a set is compact and f is defined on a set that is continuous, then that function should have an extreme point. Now this theorem or this above theorem can be used to locate the points where extreme values will occur. Now if this S is not compact, there may be no extrema. So remember that whenever a surface is compact, it should have extreme points. And the theorem that we studied above, that is the Lagrange Multiplier theorem, that can be used to locate the point where the extreme values will occur. We are having an example here. Let S be the unit circle. X1 square plus x2 square equal to 1, and define G from R2 to R by G of x1 comma x2 equal to ax1 square plus 2bx1 x2 plus cx2 square, where a, b, c belongs to R. Then S equal to F inverse of 1, where my f of x1 x2 equal to x1 square plus x2 square, right? So we have defined the surface and a function g. Now we can find what is del f of x1 x2. Now del f of x1 x2 equal to x1 comma x2. Now what it should be 2x1 comma 2x2, right? 2x1 comma 2x2. And what is del g of x1 x2? G of x1 x2 is again x1 comma x2. Next we want to find its derivatives, right? So 2a x1, so it will become 2a x1 plus 2b x2. x1 x2 term is there now. Next term is 2b x2. Sorry, 2b x1 is there. So 2b is not x2, is x1 plus 2c x2. So this is the del g of this p should be equal to some lambda times del f of p for p belongs to S and P is equal to x1 comma x2. That is if and only if it will occur if and only if the coordinates should be same. That is 2x1 is equal to if and only is we can write 2ax1 this time 2ax1 plus 2bx2 should be equal to what? Lambda into this, right? So lambda 2 lambda x1. Similarly 2cx2 plus 2bx1 should be equal to 2 lambda x2. Or we can have its matrix form as A, B, here on the reverse, right? First I should write x1 term. So B, C into x1, x2 equal to lambda into x1, x2, right? Now what does this means? Ax is equal to lambda x form, right? So Ax is equal to lambda x form, which implies this x is an eigenvector, right? This we have studied in your linear algebra class. So in the same way, here what we are getting is this is an eigenvector. Thus the extreme points of G, thus the extreme points of G on S are eigenvectors of the symmetric matrix what is that? A, B, B, C. Note that, so in order to find this extreme point, we want to find what is the eigenvalue. So note that if x1, x2 is an eigenvector of the symmetric matrix A, B, B, C, then ax1 square plus 2b x1 x2 plus cx2 square, this can be written as x1 x2 into, converting everything into matrix form, A, B, B, C into x1 x2, right? Now this is equal to x1 x2. I can replace this with see, having this as lambda times, right? So this is equal to lambda times, so marking this as star and all, means this can be written as lambda into x1 x2 by star, right? Now this is equal to, lambda is a scalar one, right? So lambda into x1 square plus x2 square, right? Now what is x1 square plus x2 square? It's given as unit circle, right? See, x1 square plus x2 square is equal to 1, given x1 square plus x2 square is equal to 1. So this will become lambda into 1. So that's equal to lambda. So we got what is your lambda here. So the eigenvalue lambda is, so the eigenvalue lambda is g of p comma p equal to x1 x2. Since a 2 by 2 matrix has only two eigenvalues, these eigenvalues are the maximum and minimum values of G on a compact set S. So the eigenvector lambda is a G of P itself, right? So since a 2 by 2 matrix has only two eigenvalues, these values should be one is the maximum or one should be the minimum. There were level curves of the function. So let us examine what is this G is. The level sets of level curves, not set, as level curves of the function G, where G of x1 x2 is equal to a x1 square plus 2b x1 x2 plus c x2 square comma ac minus b square greater than 0 are given as we can say that this is going to be, I'm drawing my axis like this. So exactly this will represent the ellipse, right? So it will come something like this. Okay, so many ellipses like this. So made a mistake here. Okay, what we're getting is so many ellipses. That means an ellipse like this, right? Another one. Okay, a bigger one. Another one. So many ellipses will come like this. So from this, we can consider a circle also. Okay, so that circle means somewhere it may come something like this. Suppose I am getting a circle like this. So we will get some intersecting points here, 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 and here, right? Now the 4 points where these curves are tangent to the unit circle are the extreme points of G on S. So when you consider this as unit circle, so the 4 points, where the curves are tangent to unit circle are the extreme points of G on S. So this is the idea of how we can get this extreme points. Okay, so with this I'm winding up today's session here. Thank you for your patient listening. Thank you.